So yeah, thanks for sticking around to the end here. As the slide says, we're going to be talking about processes and threads today, taking a look at Resque and Sidekiq. I am James Tabs. You can follow me on Twitter or talk to me afterwards or any of those sorts of things. Clearly, like, we'll be digging into these topics shortly, but really, like, if I have one point, like, there's one thing that you leave this talk with today, I want it to be this. I think, like, we're all here because we want to improve our graph, right? We want to be better at writing code. And so I want to start with a quote from one of the great writers in all of the South's history, William Faulkner, with a little advice on how to be a better writer. It's reading. Read everything. Trash classics, good and bad, and see how they do it. So my goal today really is, like, I want to understand a little bit more about processes and threads, and kind of a general introduction to those. But I want to do it by reading a couple of what I think are the classics. So we'll take a look at some of the source code from Resque and Sidekiq, kind of see how they do what they do, why they do what they do to do the thing that they're trying to do, all of those sorts of things. So let's jump right in. How many people in the room have used a Resque or Sidekiq sort of thing? Most people, okay, good. Those of you that have, how many of you have actually, like, taken a look at the source code sometime? Relatively few, awesome, okay, good, you're my target demo. Great, so really quickly, for folks that aren't familiar with a Resque or a Sidekiq, here's the rough idea. They're both background worker systems, and what background worker systems are all about is offloading some work from your Rails app or what have you into a background process that can run kind of out of the main. I think the kind of simple example is sending email, right? Your user signs up to your website, you don't want them to have to wait around for you to actually send a welcome email before they see their welcome page. So send the welcome page back, throw an item of work representing, hey, you need to send an email to this person onto a queue, and let your workers handle it. So roughly the architecture is, you have a Rails app or a cron job or one-off scripts or whatever that's throwing some work in a queue system somewhere, and some workers will pull from that queue and actually perform the work. Resque and Sidekiq are two very popular solutions in this space. The thing they have in common is that they use Redis for their queuing system. In fact, they use the exact same, well, not exact, but the compatible Redis interfaces, so you can queue jobs with Resque and run them with Sidekiq. The thing that really differentiates them is the way they use processes and threads. So, like, that's what we'll be looking into today. That's the overview. Let's start by talking about Resque, since it was first. It was developed at GitHub around 2009. Basically, the problem they were facing is, you know, they had a ton of background jobs doing all number of things, and were kind of pushing every single solution they tried to its failure points. So at one point, they're like, well, we're just going to have to roll around, but, like, what's out there, what can we use? Essentially, like, there were a couple of hard problems here. One is handling queuing. But Redis is a thing that exists, it is awesome, and does queuing pretty well. So let's use that to solve all of our hard queuing problems. And let's write some Ruby code to focus on the other things that we care about, which are, this is a more or less direct quote, but the ones I'm interested in are reliability and responsiveness, especially. So that sounds great, like, those are great goals. The big question is, how are we going to do that? And the answer to that question is using forks. That's my done slide joke, so please laugh at that. So feel better? Thank you. That's really not part. Awesome. Killing it. Okay, forks. Yeah, fork is a Unix system call that splits out. You have a currently running process, and it's just a way to fork off and have a new process running. I mean, it's easiest to understand what the code is, so let's take a look at that. Can y'all see that in the back there? Mostly, hopefully. I'm seeing some nods. Oh yeah, can we turn the lights off or down or something? Is that the thing that we can do? Is it coming down? I'm going to assume no and apologize. However, all of these slides will be up online later. Feel free to take a look at them afterwards. Yeah, so basically what's going on here, there's a function to do some logging. This is going to figure out what process we're in, but our script starts off, we assign a variable, we assign A to be 1, and then we fork. And fork is sort of interesting in that it creates a second process. It is a call, like, fork is called once and yet returns twice. Once in the pre-existing process called the parent process, and once in the newly created process called the child process. It returns a little bit differently. In the parent process, it returns the ID of the newly created child process. And in the child process, it returns nil. So, like, that's not the only way to use fork for Ruby, but, like, that's the pattern that Resque will use, so I wanted to expose you to that. So the way to read this then is that first block, we fork, we look at the return value from fork, assign that to PID. If we got something back, then we're in the parent. Right? We have the ID of the child process, so what the parent process is going to do is just print out, I'm waiting for the child, wait for the child, and then only once the child is done, it'll print out done with the fork and the value of A. That variable will be assigned before the fork. On the other hand, if we are on the other branch of the fork, we're in the child process, we're going to print out the child is doing work, we're going to sleep for 1 second, just wait, increment A, and then print it out and then exit. So think through that for a second and imagine what that might print out. Turns out when I ran it, it looked something like this. I guess we are not guaranteed of the ordering necessarily there, but the parent process does wait for the child process to finish. So it's going to wait for the child process to sleep and increment and print out. And really, I think the key point here is when the parent process exits, like shortly before the parent process exits, it prints out A is 1. So even though the child process could see the A that we created beforehand, it does not, like it gets its own copy of A. When the process forks off, it has the entire memory state the parent had. However, it maintains its own separate isolated copy of memory. So updates in the child are not propagated back to the parent. That's an important distinction. That making sense to everybody? Any questions on that? Feel free to ask questions anytime. It's just so yeah, in this model, this is again not the only way to do forking, but in this model, the child process springs into existence, does the one little thing real quick, and then dies. And again, we'll see that's kind of how Resque uses that. So let's actually dig in. Let's read some code. I have prepared a quick little example to dig in here. When I say read, I don't mean read. I mean explore. Like we have much richer tools for reading code than literally cracking open a file and reading line by line from the start. So I'm going to let's jump in and pry around and look at some of the source. So what I've got here are a couple of tools that I wrote just to make this a little easier. I've got a pry job that all it does is binding.pry. If you don't know pry, it's like a debugger sort of thing. So I'm just, I think the big question here is we'd like to understand how, once we get a job put into the queue, what happens? How does that get executed? So let's just do it and see what happens. I've got a couple of scripts here. There's a queue script where I can just quickly enqueue jobs into Resque and Sidekiq, and again, pry job just does a pry. So I will queue up into Resque a pry job, and over here I will start Resque. I swear I can type when people aren't watching. They look away. So you never even see that. I can't actually make this one bigger. You good? Back? Cool, thank you. Alright, so here we are. At some point in our Resque process, that job got pulled off the queue and is running and has hit a pry point, and so we're paused and can inspect things. So let's see how we got there. I've got pry stack explorer, so I can see the backtrace. That's good. So again, we've got some setup there. Reading from the bottom, there's a bunch of things that involve rake somehow. They're presumably the rake task that I ran. The first thing that looks relevant to my eye would be this first mention of rescue here. I guess we could start one frame up. So let's go to frame 6 and poke around. Here's frame 6. Anytime you're in pry, you can type where am I to give yourself some context. -F for the whole file that you're in. -M for the method. This is a rake task, so it's a little weird. You basically use the shorthand, and @ is short for where am I, just to explain that. So anyways, where am I? I'm here in this rake file. If I look for a little bit more context, this is the rescue work task that news up a rescue worker, sets some stuff from the environment, and then eventually calls worker.work, passing in an interval. So let's step down that call. Here's the work function, and really this is the centerpiece of rescue. So if you understand this method, I think you pretty much have the whole thing in your head. Let's see the whole thing. Not the whole thing because Zoom, but close enough. Okay, so the work function. When a worker starts working with some sort of interval, what does it do? It doesn't start with things, which we could go look at, but the main part is in a big long loop, check if we should shut down, break out of the loop, presumably proceed on to shut down sorts of things. If not, we are going to reserve a job out of the queue. This reserve literally just pops something from a Redis queue and gives us a job object. And then it will proceed down into a fork. So we fork. If we have a child process, we're in the parent process, we're going to do a few things to update the line, the process status line, which we'll see in a second. But the heart of that is the same thing we saw earlier, where we're going to wait on the child to exit. And really not do much else. The parent process just sits there. The child is the one that sets up some signal handlers, reconnects to res, and then actually performs the work. So if we step down, we should be right there. In form call, as we are. Down again. We're running, I should say, job here. Job is a rescue job, which represents the thing we got off the Redis queue. We step down a little bit farther, and we'll get where we are. This is the perform method on the job class. So again, the job is just a wrapper around the thing that was on Redis. So that unpacks it, and grabs the payload class, grabs the payload args. In this case, I didn't have any args, so it's just nothing. And then job here is the literal job class that I defined. It calls perform on the job class, which is the way Resque asks you to implement jobs. Passing in the args, which here are empty. And proceeds down to a little book that I wrote so I wouldn't have to do separate things for Resque and Sidekiq, which was probably a really terrible idea. And then into the perform call. So that's the whole thing. Any questions about it? The general sense of it? Cool. So one of the things I want to point out here is that we have forked off to work on a child process, but we really, there's one big long loop that goes, grab a job, fork to perform the job, and essentially that's it. So while this job is in motion, it's essentially hung, right? We're waiting on surprise to exit at home. So if I try and enqueue other jobs, I have a tick job that just counts down. If I try and enqueue that, nothing's going to happen, right? Because that one rescue worker is basically, I have no concurrency at all right now. But one of the nice things that Redis supports is that the parent process can take signals. If I use PS tree and grep for things containing rescue, PS tree is the process tree, so I can see my full process listing. Here are the processes I have running that involve rescue in the title somehow. If you're not familiar with this stuff, don't worry too much about it. The first one is just the grep command itself. But these last two are the interesting ones. This is the parent process. This is the rescue worker that I booted up to begin with. It's set its proc line to indicate what's happening. And that parent process is saying, hey, I forked off a child with this process ID at this timestamp. And the child process is telling me, all right, well, I'm here processing specifically a pry job since this timestamp. And one of the really nice things is Resque supports signaling. So there are several signals that it will respond to, but I can use kill. Kill is really for sending any sort of signal, but I can send a user1 signal to this parent process, and Resque will receive that signal and interpret user1 to mean, all right, worker process, the child, like your child that's currently working on something, is hung, kill that process, and then go back to the queue and start consuming again. You can also send signals for gracefully shut down when you chance, hard shut down, all those sorts of things. But if I send it a kill, if I send it a user1 signal using kill, it should, thank you. Through that process, it kills the pry job and then picks up the next time. So again, two important things there. Nice sort of signal handling to coordinate with workers, and also realize that Resque does not give us any concurrency. We can only process one job at a time. If you do want to process more than one job at a time, which you often do, you'll need something else. Lots of options. You can use a monet or a god or something to spin up several workers. There's also like rescue pool, which I have here. I've got rescue pool configured to start up 3 workers. Sorry, that's a little hard to see in this resolution, I apologize. But again, you only get one active worker per process that you have spun up. So if I now enqueue into rescue for tick jobs, I have 3 workers running. Those 3 will grab work and start performing them. There's still the queue's a little backed up, so there's 1 job remaining. Those 3 should finish up shortly, and then 1 more will grab some work. If I look at the tree, it reflects what's happening there. Rescue pool itself has forked off 3 rescue workers. Each of those rescue workers are each of those, every time it consumes a job, will fork off a child to perform that work. Now, how people do it? Does that all make sense? Big question then, if that's how Resque is working. Oh, sorry, I guess it's somewhere. So, big long loop, starts up, initializes, registers signal handlers, grabs manual work, forks off a child process. The child process is the thing that always does the work. The parent process is always there, just waiting. So, Resque in one slide. The question then is why? And this really is a non-rhetorical question. Does anyone have an idea why we would want that sort of architecture?
Quick question before we
Sure.
When you fork a process, is it reloading the entire Rails environment?
Excellent question. Yeah, like we saw a little bit of a sketch of that. We had that a equals 1 variable and then forked off, and it read it. So no, when you fork a process, it gets a copy of like all of the existing memory in the parent process, and you might be a little concerned about if that's a lot of memory, you're making a big copy. But most modern systems will implement a copy on write where you don't actually have to copy the memory unless you are changing something. So usually it does the right thing. But like if you are changing things, you will have multiple isolated copies of the memory. Yes?
So I have another question. So how do you queue up the stuff that's busy doing this process?
Oh, so like that's the nice thing is you're decoupling doing the work from viewing the work. So like as long as you can contact, you don't have to have any workers or anything whatsoever. As long as you can throw like a JSON string into Redis, you're queuing up the work. So it can be consumed at any point in time as long as Redis is up, you can queue up the work. Yes?
Your question about why would Resque operate that way before the process, any changes that the job makes to the global state will not have an effect on the parent process when they separate the global state and then incorporate and modify.
Yeah, very much so. That's definitely one of the big ones. I think Resque says it well. Resque, again, born out of chaos. Like battle hardened at GitHub, and they really are assuming the worst because they had seen a lot of it apparently. So really, forking gets you 3 big things there. It mitigates the risk of leaking memory. Like if your jobs do something bad, that's okay because they're going to run in a child process that when it's done, it exits and cleans up after itself regardless. You avoid the cost of booting Rails for each job, right? Because the forked process gets a copy of its parent's memory. And because that parent process isn't doing much other than sitting there, it should be responsive, it shouldn't hang, and you should always be able to reliably send signals to the parent process to do things like shut down the child if the child is misbehaving. So that's nice. That's all well and good. Rescue's great, my talk's over. We know I'm going. But wait, Sidekiq's a thing, right? Sidekiq's a thing. Why is Sidekiq a thing? I'll use some direct quotes. And in fact, actually, Mike Kern, the guy who wrote Sidekiq, is here. So, if anyone wants to direct hard Sidekiq questions, like, so I feel weird quoting you right here, but I'm going to do it. So, Mike Kern's Sidekiq, I think it sounded to me as though it was explicitly a reaction to Resque. And I was like, the problem there, with Resque, you have some safety because you are sandboxing all the processes and not sharing memory. But that means if you're running 20 workers, you might need your Rails app size times 20 amount of memory. That can get pretty expensive pretty quick. With some auxiliary goals of a monorepo system that's high performant, well supported, and includes some of the batteries that like Resque has in the ecosystem in terms of gems, but even aren't quite baked in, like automatic failure retry, scheduling jobs, things like that. So, again, noble goals. How are we going to do it? And the answer to that one is with threads. Here's my other bad joke picture slide. It's a little better. Thank you. Appreciate that. Yeah, so we'll be using an underlying mechanism called key threads, but probably won't be thinking about too much. Here's the thing about threads. They share memory, which is cool, until it isn't. And seriously, that's the idea, right? Like, you want 20 workers performing work. If you're on Resque, that means 20 processes and 20x the memory. It'd be great if you could have 20 threads doing the work. Like a thread is very similar to a process, it's just threads don't have their own isolated memory space. Which can lead to some really subtle, hard to reproduce, hard to track down bugs. Here's a rough sketch of one of those for anyone who hasn't had this particular bug before, of a race condition sort of thing. So this is a parsed down example, but like pretend you're a bank and your clients have wallets and you're tracking money for them, and you decide all of your banking software is too slow, so you're just going to run everything in a thread. And it'll be fine, right? Because those are like nice atomic operations and nothing's going to go wrong. it'll be fine. So the thing about threads is the OS scheduler is required to make sure that all of the threads running on the machine, like the ones you write and all of the system threads, kind of all have their fair share, like of access to processor time. So it is free to pause and resume threads more or less as it sees fit, which, you know, it's fine for processes because they have their memory, but you get weird bugs with this sort of thing. Really, because of the scheduler, anytime you see multi-threaded code, you should just randomly insert sleeps for random lengths of time in your code everywhere, and ask yourself if there's any possible way that it can go wrong, and the hint probably is there is. So, you know, imagine something like this. Depending on how long things get paused for, and what runs in what order, and who gets to the finish line first, since the race community, you might end up with one thread reading that there's $100 in the wallet, going to sleep, the other thread waking up, decrementing it to 90, and then the first thread waking back up and going, okay, 100 plus 10 is 110, good, you have $110, and now you're a bank and you're out money, and that's not a good thing. You doing as a bank. So that's a very parsed down, like, kind of prototypical example of a reason to do different sorts of things. And the worst thing, like, it's totally non-deterministic, right? It's entirely on the whims of the OS scheduler, so it might happen very infrequently, and it's a nightmare to debug. So, like, we'd like to do something better. And the answer to that is, well, one answer to that is something called the actor pattern that's available to us in Ruby using a library called CELLULOID. Very much influenced by Erlang and some of its ideas. I think kind of the key idea here is what makes a lot of this stuff really hard is that our primitives for talking about objects and our primitives for talking about concurrencies are unrelated. And so we have to manage them independently and always mess up doing that. The actor pattern is a way to make that a little bit easier. So here's what this might look like with something like CELLULOID. If you notice, it looks alarmingly like just a plain old Ruby object. I have a wallet class, it's got an amount that it keeps up with, some functions for adjusting that, an reader at the fancy, and just include celluloid. And that gets us remarkably close to everything just working. So we just new up a new wallet, we can asynchronously adjust. Like this is how Sidekiq handles asynchronous method calls. And we still can make synchronous method calls like calling wallet.amount. Under the covers, what that's doing is kind of a lot, actually. When we new up a new wallet, we in fact do not get back a wallet. We get back a celluloid wrapped wallet object. And really, it turns this wallet into an actor. And what that means is it's going to be an object that's running in its own thread. And where all of the method calls, like all of the messages sent to that object, are mediated through a celluloid mailbox. So when we make a call, what that's actually going to do is just going to throw that message onto a mailbox that celluloid will handle, the synchronization of. So when we asynchronously say to adjust by some amount, that's just sending out a piece of mail that the wallet will eventually get and process. So that, I think, that seems reasonable enough. There's a bit of a question then, okay, like you've got this wallet running in a separate thread, how do you then do a synchronous call? Like how do you get data back out of it? But these async calls are fire and forget and will immediately return nil, and often you would lose insight into if an error is raised somewhere in there. So for celluloid to make a synchronous call, it sets up kind of a return to sender mailbox. Right? So you make the call, it goes to the wallet's mailbox with a respond to, and the wallet, when it's done, it gets the amount and sends that back to the async proxy. This is, again, just an object that celluloid will take care of for us. And the caller will sit there and block and wait for a response to come back in. So, that's kind of the underpinning technology. I think hopefully you see that makes it really comparatively nice to write multi-threaded code because it really very much just feels like writing good plain old Ruby objects. So let's dig into Sidekiq a little bit and see exactly how it does it. So same strategy here. I'll start up a Sidekiq instance, and I add a little rig test for consistency. So same idea. Keep that up. So here we go. At some point, that got pushed onto a Redis queue. Sidekiq pulled that off, and we are now in that perform call somehow. So let's see how we got there. Okay. Again, like there's some celluloid stuff in the background here that I probably don't care about immediately, but we'll want to get back to. So I might start from the first mention of Sidekiq, or maybe one up from that again. So let's check out frame 14. This would be the celluloid, dispatching that method. So variables I have here. Object is a processor. Processor is a Sidekiq processor object. I'm sending the method process to it asynchronously. And here's what that does. I step down, that ends up here. Say, where am I? Look at that method. So here's the processor's process method. It takes some work. Work here is a Sidekiq basic fetch unit of work. I think pretty clearly represents, it's an object wrapping the JSON data off of res. So I'll get that work, I'll do some stuff, and end up here, calling stats, step into that. That's just updating some statistics. So continue down. Here I'm now in the middleware chain, which is pretty cool to see how this is implemented. Yeah, let's just step through it. So if you're familiar with like rack middleware, it's essentially the same sort of idea where I can implement lightweight wrappers and compose them together. So if I step down through this chain, I end up at one piece of middleware, the Sidekiq logging middleware. And here's the entire file. It's one call method, and this is responsible for logging around jobs. And it's just like, give the logger some context, start a start time, log start, and then yield to the inner middleware. And then print out when we're done or if we failed. So continue down, next piece of middleware. This is the retry jobs middleware. And if taking a look at the call function here, it's going to yield again to the next layer down, but rescue from exceptions and attempt to retry the job. This is the thing that we'll retry the job after X seconds, and then 2X seconds, and then 4X seconds, and so on, up to some configurable limit. So on down, and finally we get to execute job, where we pass in the worker, which is the literal class that we defined, and that's called worker.perform. And we end up back at our RI session. So that's interesting. It's good to see that architecture. I don't think we saw much of the multi-threaded stuff though, because if we look at the stack, we started inside the actor for the processor. And presumably, this work got to the processor from something else that's not quite as introspectable from the stack trace. I'm just curious, any thoughts about if you wanted to trace down, how did that work get to the processor? Where would y'all look next? Actual non-rhetorical question. Well, okay, here's what I would do. Yeah, so we saw that whole thing started off with an asynchronous call to a processor object sending in the message process. So given what we know about the celluloid API, presumably that was somebody called .async.process. So I'm going to open up that gem bundle open and grep through it for that string. And here we go. There are two places where that match, and one is processor done, and that's probably not it. So I think we get pointed to this file. This is the Sidekiq manager. Might be interesting to see how that boots up. When we initialize a manager, it's going to figure out how concurrent it should be. If it's 25 many concurrent, it will 25 times boot up a new processor, a new link starts a new actor, and then kind of monitors that actor to see if it crashes. If it crashes, it can trap the exit of a linked actor and call processor died, which would restart a new processor. So we'll spin up those processors, and then the actual async process call comes in assigned, which I think you can trace back through here. Oh, sorry, let's do the trap. Trap exit. So when a processor exits, we'll call processor died. When that happens, we'll remove it from our internal list of processors that are available, and unless the manager itself has stopped, create up a new one, add it to the list of stuff that's ready, and then dispatch. If you look at dispatch, that will immediately make an asynchronous call to tell the fetcher, hey, choose fetch. Fetcher's over here in fetch. I know this is kind of quick, so so the fetcher's going to fetch, which is a nice strategy pattern here. We call fetcher.fetch. It's going to look at its strategy and retrieve some work from here. That's the thing that got us our basic fetch unit of work from Redis. And then asynchronously call back to the manager to assign that work. And then that closes the loop, right? The assign work function was the thing that called processor.process and got us to where we were. So that's how jobs get run in Sidekiq. So that's the how. Any questions on that? All right, well, sorry, yeah.
So it's using Fred, or is it some other?
Excellent question. MRI has a global interpreter lock. So you, depending on exactly what you're doing, you may not see much of a speed up from threads there. It's really quick. Like, if you are processor bound, then MRI threads are not going to be able to utilize extra processors, and they're not going to see much speed up. But I think a lot of jobs are normally IO bound, so you can see some extra throughput even with near. But yeah, like if you want true threads, you should be on a Ruby or Rubinius or something. But it totally works on MRI. Yeah.
Just to clarify, these are real native threads. There's only one time to these.
Correct. Yes. I'm sorry. Yes. So some takeaways. If you are memory constrained and don't want to use a lot of memory, you should use Sidekiq. If you're not thread safe, you should use Resque. If you're both, sorry. I don't mean to be glib. That just means like you're going to have to spend some time/money somewhere, and it's up to you whether it's scaling out extra boxes for Resque or spending some hard engineering time making things thread safe. If you're worried about thread safety though, CELLULOID, good place to look. Other considerations if you're weighing Resque versus Redis, how important is job isolation? Like, do you need to be able to signal them individually? What really is your bottleneck? And especially like if you're on MRI and processor bound, you're not going to get much of a speed up from threads. Also, how important is support? Mike's pretty awesome and is around. Resque, I'm not sure, and I hope no one forces me. But like the code we saw was from the 1.3 branch. There's been a 2.0 branch around for forever, and I don't know if it's actually going anywhere. Haven't seen a lot of activity on it lately. Someone correct me if I'm wrong, but that's what I've seen. Other things, and again, I think maybe more important than specifics about processes or threads. Don't be afraid to jump into some code. We have lots of great tools for doing things that are better than just reading, like pry, lots of utilities. Everybody know about WTF and pry? The more exclamation marks you put, it's the backtrace of the last error, and the more punctuation you have, the longer backtrace you get. It's my favorite way to think of it. But yeah, we have lots of great tools, so lean on them. And also, like, try open a good gem sometime. Like, if you're interested in these sorts of things, Unicorn does some great Unixy magic stuff with forks and self-pipes and whatnot. Resque Pool, actually pretty much the same thing as Unicorn, if you look at the code. Adhesion is a big telephony thing built on top of Celluloid. And I gather Ben Playing is speaking tomorrow morning, so you might ask him about it. He's done a lot of work on that. Also, if you want some reading, these slides will be up on GitHub. Also, some links for blog posts. There's one diving into Unicorn and structure I think is quite interesting. And then a few more on specifics about thread safety and Rails and global interpreter lock and those sorts of things. That's all I got.